Right, so my name's Anthony Marcar. I work at WalmartLabs as a Clojure developer, and I'm going to talk a bit about Clojure at scale. So when I talk about Clojure at scale, I'm talking about, we've kind of been using Clojure at Walmart for about 3 years now. Like a lot of people in the Clojure community, when you're operating at a little bit of scale, larger than normal, it's a bit of a frontier. There's a lot of tutorials out there on how to create small Clojure applications, little libraries here and there. But in terms of resources on how to create larger applications, that's something that we didn't find too much of. So this talk is basically about our experiences that we've had, some of the, I guess, things that we've been able to find out that somewhat work. So I don't want this to be like, this is how you should do it. This is just our experiences and recommendations that we've come up with. Everyone should be doing these things differently. It's a frontier. But anyway, this is what we've come up with. So a little bit about our system. We run a team called e-receipts within Walmart. To the customer at a store, it's a few things. It's basically every receipt that's printed in a store has this QR code down the bottom. That QR code encodes the unique identity of a receipt so that you can scan it with the Walmart app or any app for that matter, and it will download that receipt onto your phone, associate it with your account so that you can now do returns. You'll never lose that receipt again. In the future, we hope to go purely paperless with this as well. As well as that, there are some other teams within Walmart who can use this information to provide other benefits to the customer. Savings Catcher is basically getting money back if it was cheaper at other stores. InstaWatch is getting a digital copy of a movie that you purchased in a store. The 1 Hour Guarantee is the largest sale in the world. And all of these kind of partners inside the company use our data as well. So within the data center, where it starts to get more interesting, so we have approaching 5,000 Walmart stores, I think now. We get data from all of those stores. Every time a receipt is printed, that transaction is sent up to our data centers, where a whole bunch of stuff happens, a whole bunch of side effects. These could be saving it to the database. It could be forwarding it on to other partners within Walmart. It could be sending push notifications to customers. It's essentially just a one-way pipe of data coming in and stuff happening. So, of course, in the internals, we use Clojure. It's essentially a one-way directed graph of data. We have durable queues in between all of our consumers and producers, so that because when you're operating in a Walmart data center, stuff goes up and down and goes missing, and everything that Zach was just talking about is very true, especially at this kind of scale. So at all the edges, we have queues. If Apple is down, which I hope it wouldn't be, but if it does, then we actually have a queue that kind of blocks, protects us from that bit of realm, and vice versa for all of these other side effects. We have a lot of other Clojure as well. We have Clojure to do REST APIs to cold access. We have Clojure to do deployments. We have Clojure to do monitoring. It's Clojure all the way down. We use a lot of Clojure. All in all, this is about 20 services that we run. It's about 50,000 lines of code. It's about 70 Leiningen projects. These are all ways to get a sense of roughly how big it is. I don't think it's the biggest Clojure system out there, but it's a little bit bigger than normal. And we run this with about 8 developers and have been doing it for about 3 years. It all started from a Java application back in a startup, and then we've rewritten it all to be big and Clojure-y, yeah. So basically the stuff I want to talk about today is all the things that we run into as we grew the team and grew our code base. How do you structure code? How do you deal with multiple projects, like Leiningen projects? How do you evaluate what libraries to use inside your applications, and a bit of a framework for thinking about that? And also just embracing the Java ecosystem. We build on the shoulders of giants. Java is painful to write, but there are a lot of awesome technologies there. And it's easy when you come in from a non-Java background to kind of like be scared of all that Java stuff. But when you reach these kinds of scales, then Java becomes your friend. And if I get time, every time I give this talk, it goes a different length. But if I get time, I'll go and talk about infrastructure as code as well and some of our ideas around that. So yeah, structuring code. There are a lot, as I mentioned, there are a lot of tutorials online, little quick namespaces showing you how to write applications. Almost all of them have def, connection, start connection, and then functions that kind of like reference that global state. One thing, this is how we started. Over time, we've tried to eliminate as much global state as possible. And a lot of this is driven by Stuart Sierra's talks on Clojure in the large and component. And basically the recommendation I can give that has worked really, really well for us is embrace component. If component is a library, it's a tiny framework that helps you manage runtime state and gives you a place to put it so that you can instantiate it, you know where it is, and it's not just kind of some global var sitting off in the distance. So I'm going to show a little bit of code about examples of how we actually use component. Before I do that, who is already using component in some way? Okay. So I'll walk through a little bit of how component works then and what it is. So this is a component. This is a Cassandra component that we have. It is essentially holds a database connection and configuration on how to create that connection. So it's just a record in this case. A component can actually just be a map. It's basically just some place to put data and so on. So we have hosts, which is just going to be a vector of IP addresses where the Cassandra connection is. We have a key space, which kind of tells us which key space we want to access inside Cassandra. And when we first instantiate this record, we don't give it a connection. The connection is something that we want to be put into this record after it started. So how does that happen? So there is this protocol called lifecycle in component. And component provides two methods, start and stop. You call start, and we're in Clojure. It's immutable, so this is going to return a new version of this record. The old version still exists, but after we call start, it'll go and do all this work to create a Cassandra connection, and it'll return that by just associating the connection back onto this record, and so that's what you get. This isn't some kind of immutable thing that you call start on, it mutates the state inside, and then you just keep the same reference. Every time you call start, you need to grab the result of that. And component gives you ways to do that very, very easily. So within here, we say when we call start, if the connection is on this record, that means it's already started. And we want to do idempotent operations here. So we are going to just return immediately. We're just going to send back the same record as we started with. If it hasn't been started, if that connection object is nil, then we are going to call this start connection thing. That could be whatever. In the case of Cassandra, it probably just returns a connection object. So we're going to associate that object back onto the record and return the record. Vice versa for stopping, we have, if the connection is present, it means that it has been started, so we do want to stop it. So we're going to call stop connection, which does something, stops the connection, and then associates connection back on as nil so that we know that this is not started anymore, it's stopped. And vice versa, if the connection was nil, that means we're already stopped, so we can just return the record as is. And for each of these components, we usually just have a helpful constructor. In our applications, there is a config map. It's like basically an Eden file that sits on the machine and is loaded when the application starts. And this config contains all the configuration, like IP addresses, usernames, passwords, all that kind of configuration. We throw that into the constructor with a key space, and then this constructor is responsible for pulling out the information from that configuration map that it cares about. In this case, we're going to assume that config is a map. It has a key Cassandra, and under that, it has a hosts map, or whatever it is. And so we use that to call the record constructor and pass in that information that we need. So this is what a component looks like for us. And there are different types of components. If anyone's seen Stuart Sierra's component talk, he talks about 3 different types of components: stateful, service, and I think it's composite or something like that. This is an example of a stateful component. There is some state. State could be a database connection, a thread pool, an atom, like anything that is inherently not immutable. Even a core async channel is state in some way. So that's what this does. This is encapsulating that state somewhere that we can think about and reason about and instantiate. Another type of component is push. So this is a service component. It kind of encapsulates some service over here which does something. In this case, it's an HTTP SMS service that we might use to go and send an SMS to a customer. And by the way, most of this code is actually really close to how it looks in our code base, like in our production code. So in this case, you'll notice that we have a record. This is our component. It has a little bit of configuration, a host and a port that we want to go and send information to. And we have naively decided to use a blocking HTTP client, which doesn't give us any kind of access to that connection or how to stop and start it, but that's fine. In this case, there is no lifecycle. So we're just going to say a record is constructed. It doesn't need to be started or stopped. It's just a record. And what component will do is it will say, all right, well, if there is no lifecycle created for this particular record, then we're just going to return the record. There's nothing to stop and start, and that's fine. So in this case, we just have the record, and it's just implementing a protocol, which is just going to send an SMS to a customer, given a phone number and a bit of text to send them. And again, we just have a constructor function just to make our lives a little bit easier. We pass in a configuration map. It's going to pull out the SMS configuration from that map and use that to construct the record. So that's that kind of component. That's a service component. The last component that I'll mention is a composite component. And this is, you can think of it like a business logic place. We've got our kind of underlying components that deal with state, service providers, all these kind of raw operations that we want to do. A composite component is something where you can actually put in the business logic. So this one, again, it's a record with no start and stop because there's no state we care about. We're going to give it a little bit of configuration, some text that we would want to send in the SMS. And then we're going to give it some components of its own to use. In this case, the Cassandra component because we need to persist receipts, and SMS because we need to send messages to customers. Here's our constructor. This one's a little bit different. We've got our usual calling the default the constructor for the actual record up here. Inside the uploader in that config map, there's going to be that SMS text, we presume. But also, you'll notice that we're using the component system to say, you're going to need a Cassandra component, and you're going to need an SMS component. We're not going to tell you what they are right now. Like, you don't have to construct them before you pass them into this new uploader constructor. We're just going to assume that there is some component that has been created, which you can reference by this name here, receipt Cassandra, and there is also going to be some component called SMS. So when you find those, when component tells you what they are, and this is just classic dependency injection, just slot them into Cassandra and SMS up here in the record. So finally, we end up being able to use these components. In this case, we have an upload receipt function. Basically, when a receipt is uploaded into our system, we need to go and do some stuff. And that stuff is going to be inserting the receipt to Cassandra and sending an SMS to the customer. So the important thing here is that we've passed in the uploader component into this function. Usually what you'd see is something a bit like this. You have, called old upload receipt, because this is actually what we used to do. We would call this upload receipt function, we would pass it the receipt, and then we would just assume, I shouldn't go to that meeting. I thought I'd turn off Outlook. I did, all right. Yeah, we use Outlook at Walmart. You're going to insert a receipt to Cassandra and you're going to send an SMS. But you'll notice that we haven't told it what that Cassandra object is, where the connection is. This is kind of very typical code that you'll see around the Clojure community where it is assumed that there is a connection object in some namespace that has been started. But we don't know. And so if we were to just call this function as is, who knows what might have happened? That connection object might have been stopped. There might be some kind of race condition that occurs there because now it's like a single bit of state that everyone's trying to use. So there's a lot of problems with this. And while the code looks nicer, there's less destructuring of kind of various other subcomponents and so on. It does hide a lot of complexity that's going on here. So this is how we write it. We pass in the uploader. We pull out the information from that uploader that we care about, which in this case is the SMS text configuration, the Cassandra object, the Cassandra component and the SMS component. And so therefore now, the Cassandra function just takes the Cassandra component and does something with it, and vice versa with send SMS. This doesn't need to know about the internals of Cassandra or SMS. It's just going to pass it through to the bit that cares, but the important thing is that we have access to all these, and there is zero global state right now. Everything is within lexical scope within this function. So we find that a huge win. So let's go one step further. How do we construct this system? Here is our constructor for our whole system. Ours is about 10 times bigger than this because we have a lot of components. But essentially what we're doing here is we are going to say, construct a system, assign these names to the various components so that we can reference them in other places, and then go and construct them. So we're going to construct the Cassandra. We're going to pass in the configuration map, which we're just pulling into this here. And we're going to say this particular Cassandra connection is for the receipt database. We're also going to construct another Cassandra component. This one's for the customer database. And you can see here we've already kind of gone further than what you could do just using a single global var for the Cassandra connection. You can't instantiate that connection multiple times. Here you can, because it's just in this record, so you just create multiple versions of the record. So for us, when we have multiple databases, and this is something which I think as code bases get bigger and bigger, you run into, this is where the advantage comes in. Another thing to note here is that we don't need to care about ordering. Component will figure out the order of dependencies when they need to be started and stopped. So all we need to do is say, we could swap all these around. We could put, Redis down here. There's nothing that, that we need to worry about here. Here's where it actually, we tell component how things are ordered. We say, this customer API component depends on Cassandra customer and store Redis. So therefore, the component will do the job of constructing those first, calling start first, so that everything is started and stopped in the right order. So this is how we construct a system. We've got services here. The receipt service might bind to port 8080. That would be kind of its start operation. And then push would usually just be like starting connections and doing various configuration. So yeah, as I mentioned, ours are a lot bigger than this, but this is how you can start a system. And I can show you what that actually looks like. Whoop. So I've got a bit of configuration here. This is pretty much what a lot of our stuff looks like. You have some SMS configuration, including the host and port. You have the SMS text we referred to earlier. Struth, you've got a receipt. We have some Cassandra hosts that we're going to care about. So this is what our configuration map looks like when we pass it into our application. And then if we want to start the system or create a system, we can call so this is this new system function which I mentioned earlier. So let's create that and see what it creates. Nothing. Oh yeah, I need to pass it some configuration. Okay. So here you can see we've created a receipt Cassandra record. It has hosts, the key space, and a nil connection. And that's because we haven't started the system yet. We have a customer Cassandra, again, with a nil connection. We have our uploader here, which importantly doesn't have Cassandra or SMS yet because we haven't started the system. So this is what the system looks like when you construct it. And remember, it's just a map. There's nothing special going on here yet. So let's take that. Let's call that system. And now let's start it. And I'm going to preprint this. Okay. So this time, we can see that the receipt Cassandra has a connection object. It's here. We can see that the customer Cassandra one has a different Cassandra object. The uploader, so the uploader now has the text, and it has a reference to the other Cassandra object. And remember, we're talking about a big persistent map here, so where it looks like it's all copied around, but this is actually just referencing the same actual bit of data. But again, this connection object is the one which was created earlier. So now we've kind of filled in all the blanks. Everything's been started in the right order. We've got our connection objects created, all of our business logic components that relied on Cassandra and SMS and everything, they're all filled in now. Like this system is ready to go and we can start using it. And just to hammer this at home, the system that we created originally is still the same thing. The uploader, oh no, wait, I deffed that, didn't I? Ah, right. The original system that we created hasn't been mutated. It's still an immutable record. So this makes reasoning about your system very easy. So this is kind of a great way to structure your applications that we've found. It really helps in testing as well. We do a lot of side effect testing. We will say, run upload receipt and make sure that an SMS was sent to a customer. Well, we really shouldn't send an SMS to a customer when we're running a test. That's not a good idea. And this is a pretty common occurrence that people run into. And usually the traditional way you do this is you would mock. You would, with redef, you would kind of take the function that you were going to run, and now you just say, instead of running it, just do nothing. Mocking libraries can get pretty powerful, but if you can restrict yourself to the core Clojure ecosystem, like the core Clojure libraries, you're going to find yourself in a much more flexible area. So what we do is we had our push protocol here, SMS. And obviously here we're going to send a post to some SMS provider. They're going to do the work of sending the SMS to the customer. So what we can do is we can, instead of creating that record, we can create our own record that still implements SMS, but simply puts that result onto a channel. And we've kind of experimented with this a little bit. You can put it into an atom. You can use various other kind of synchronization mechanisms. The great thing about putting this information into a channel is that you can block somewhere lower down the test so that you can immediately know when a particular operation occurred. As opposed to when you perform a side effect and you just put that information into an atom or something like that, you've now got a poll at the end of the test, or do a thread sleep for about 10 milliseconds while you wait for that particular side effect to occur. Because by definition, like everything we do here is, there's queues involved, there's side effects, like everything is occurring in concurrent ways. So this is how we do it. We will say, when the send SMS operation occurs, just go and put that information in a channel, and you're done. So here we have our same constructor for this particular component. And when we actually create the test, this is the full test that we're going to create. We're going to have some SMS text that we want to send the customer. We create our configuration map. We create a channel upon which those SMS information will be put eventually as part of the side effect. We're going to construct the SMS component using that SMS channel. And again, this would have been HTTP if we'd been using our usual system that I showed you earlier. And now we're going to construct the uploader. So this is, we've seen this one before. It's going to take the SMS text and blah, 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 and expect that there's a Cassandra and SMS component handed to it. And because components are just maps, we can do that. We can just say, construct this uploader. Don't start it yet, but just associate the SMS onto that particular uploader. So we're just telling it, just use this one now. So if we continue on, we're going to create a phone number. We're going to create a receipt, which is just a map for now. And we're going to call upload receipt. Now we want to test here that the SMS is sent. So now we can just sit here blocking, waiting for that particular channel event to occur, and then get the value out, and then boom, we can just say, here is phone number and text, and is it correct? One little challenge here is that if that side effect doesn't occur, then that's obviously going to block forever. So usually you want to put a little bit of kind of sugar around this to say timeout after a second, and if the timeout occurs, that means the test has failed. But that's all stuff you can add pretty easily. So I want to stress that this is the whole test. There is no global state still. Everything is here. So if you wanted to run these tests in parallel, you can do that now because you're constructing completely separate systems. If you're doing things with ports, you can just have an incrementer so that every single time a system is constructed, uses a different port. Now you can blast off 10 of these tests in parallel. You could very easily use this to generate property-based testing because this looks an awful lot like properties for all. So all of this stuff becomes very easy. You don't have to worry about states stepping on each other or different threads stepping on each other. Everything's here and you can instantiate it, which we find pretty cool. The final thing I'll say about this is I showed you the big system constructor before with all the different services. Again, we have something like 50 components or something like that. A lot of them are side effecting, and by default, when you're running tests, you don't want to perform those side effects. So what we end up doing a lot of is creating a mock system, which just has the components that we don't want stuff to happen to. So in this case, SMS and Apple and Google push. So now, the next time we run the test, because a system is just a map, like component is really nice like this. It's 200-something lines of code, most of which is comments. Like, it's really small. It's just kind of some dust around the edges of maps and records. So here we're just going to construct a system which returns a map, a record. We're going to merge in the mock components just over the top of it. So we're saying for those particular components, just overwrite them. We don't care about them. And now we can call start. So here, this is what a lot of our code looks like. We have a full system. Like, this is all the production code that we want to test, just with the very edges mocked out. And we can run upload receipt, passing in that entire system, and test like 99% of our code all the way through. So yeah, this is what a lot of our tests look like. So yeah, I would highly recommend using component if you're not already and you expect your code base to scale in any way. Even if you don't expect your code to scale, component is just a really nice way to reason about your code. And it also answers a few questions about where do you put code, which is the other thing we struggled with. Like, a namespace is not a class. A namespace is, just some place to put stuff. So one pattern we've been using a lot of is you've got a component for Cassandra. It has like insert, put, all the kind of like, local functions to it. So just put all that in a namespace and call it Cassandra. And vice versa for SMS. Like, this is a really great way to separate your application. And it also means that eventually, if you do want to split your application into multiple projects, then components become a natural way to separate that, because it's state, and state's a great way to separate things. So that is, right. So let's go back to multiple projects. So this is something which that we hit a lot of. You create a project, it's one line again project. We've looked at boot a little bit. We haven't looked at enough to kind of talk about it much, so I'll just talk about line. But yeah, you create a project and you want to split it out. And when you do, you kind of hit this problem of, all right, let's assume that we have system, we're using HTTP, let's assume that's one of our own libraries. And we want to make some changes to it. So we're going to go into it in CIDR. And let's just go and add a println. We can't. This is buffer is read only. And the reason is that it's actually in your local Maven repository. So you obviously can't edit it because it's inside a jar file. Who actually has hit this? Like, yeah, it gets really annoying. And this is a side effect of having a Maven repository and Java, which Clojure is based upon. So if you have multiple projects and you depend on one project down here, then that means that when you try and navigate into that particular project and make some code changes, it's actually referencing your local Maven repository. It's not referencing your local source code. I won't go on too much about this. I will say that it's been a pretty annoying issue for us. We don't really have any answers on how to best deal with multiple lining in projects. The only thing we can say is that we're in a better position to deal with multiple projects in the Clojure community, because a project.clj, for instance, is just data. It's just this thing that you can pull into memory, you can parse, you can pull out all the dependency lists, you can pull out the source directories, and you can just kind of merge it together to create some kind of zombie Frankenstein project. And that's something that we did, which I'm just going to show you what it looks like. This is a generated project CLJ. We've got some kind of name for it, we've got a version, but importantly, we've got all the dependencies from all of the projects in our, wow, that's a lot. When you look at it in a small buffer. Yeah, and like we have all the source directories from all of our projects, all 70 of them in here, all of the resource paths. So you obviously wouldn't want to update this every time you add a new project. So we just generate this, and I won't show the code for it. Like it's a good exercise and something to do, but you just like traverse the whole directory structure, pull out all the project CLJs, merge them together somehow. Then you can do stuff like run all the tests in your system within the one session. You can have access to all of your code in the one REPL session. Like it's kind of I don't know. It's a total hack, but you know, we can hack it. This is pretty like accessible to us as Clojure developers because it's just data that we can work with. Try doing this in Java or something else, and that's pretty difficult. Right. I've already. All right, I was going to lead up to this. But choosing libraries is something that we also struggle with a lot. How do you choose what library to use when you're reaching some kind of scaled application? There's a few ways that we think about this, but the fundamental thing is just be extremely cynical. And yeah, Rich Hickey said this best. Not everything is awesome. It's, you know, there's so many different Clojure libraries out there, but when they're there, you've got to ask a few questions. You've got to ask, does this force me into a particular style of programming, like an idiom? You know, is it full of macros? And if it is, how is that going to affect how we like build on this library in the future? Is it going to mean that we're just stacking on code left, right, and center, like simply to, you know, when we could have just cut it out and like done it ourselves? So in general, if a library does one thing really well, if it's small, if it's just input, output, it doesn't have any state, doesn't have any network connections, like parsing CSV, you probably don't want to implement that yourself. Like, you know, have at it. Go and grab a library for it. If it forces you into some kind of idiom, be really sure that that's what you want to do. Core async is a pretty good example of a library that does something which we just couldn't do. So we're quite happy to use it. It forces into a style of programming, but it solves a really core problem. The one to be really worried about, though, is any library which does any network operation. So we've been hit pretty hard by this. Let's take an example like, I don't know, accessing Dropbox or something like that. You know, if there's some Clojure library which maybe does this, and you can just kind of call it, give it a data structure, and maybe it just creates a file on a Dropbox server somewhere. If it doesn't give you timeout guarantees, if it doesn't tell you how the queuing works behind the scenes, if it's using blocking I/O instead of non-blocking I/O, these are all questions that you need to ask pretty early on, because the second your server starts to scale into any reasonable number of requests per second, these things can hit you pretty hard. Really good example, we were using HBase for a while and didn't do our research on the library that we were using. And so turned out that when we hit 1,000 transactions a second, which happens on Black Friday, and thankfully this one didn't happen on Black Friday, basically the network slowed down. Requests were only going at about 100 bytes a second or so. And so when you've got all these transactions coming in and it slows down, it turns out that our timeouts weren't working as we thought they were. We'd specified a timeout of 1 second, I think, but it turns out that there were like 4 other timeout parameters that we had no idea about. And it wasn't your typical connection versus socket kind of timeout. There was like a retry timeout. So if it did timeout, then it would retry itself, but it wouldn't show that to us as the end user. So it turns out that through a weird amalgamation of stuff, you get 20 minutes of default timeout on this library. And this is something that we found out the hard way. And it was blocking. So if you can imagine 1,000 requests a second, 60 seconds, you've got 60,000 threads open, yeah. So do your due diligence on libraries. Libraries are awesome, especially at the early startup stage. Like, just have at it. It's great. But the second you think that you're going to be scaling, then just be cynical about libraries. It helps a lot. Logging. So who is like understands Java logging? Well, actually, no, I'm not going to. There's a lot of logging stuff out there. There's Logback, there's Log4j, there's Java logging. Thankfully, there is some kind of facade right in the middle, SLF4j. Don't be too afraid of it. If you are getting to scale, then you're going to start to want to debug a lot of the Java libraries that underlie your system. And most, like a lot of the libraries that we use, which we take for granted in Clojure, like CLJ HTTP, it's using Apache HTTP. Like most of the stuff that we're using is still underlying is Java. If you don't understand how this works, then you're not going to be able to debug this in production. So yeah, like understand it. It's worth it. It gives you a lot of power. We're doing stuff now like we log, just using SLF4j logging, and then we configure appenders using Logback. So we might append in JSON to a file so that Logstash can put it up to a server. We might also append via UDP to a Remon server. There's lots of, once you're using a logging framework, these are all things that you can configure at runtime very, very easily. And I've got a few little code samples around this. So is this finished at 10:40 or 10:50? I don't know. 40, okay, cool. I have 5 minutes. Actually, I'll skip this. I will say I've got all this code up on GitHub. I've got a link to it at the end of it, so you can have a look at it. But here's some basic stuff that you should add to your application to ensure that all logging from Java util logging, from SLF4j, from logback, it all goes through the same facade. Otherwise, you're going to find yourself having a log4j XML, a logback XML, a Java util properties file. So it's really nice to kind of put them into the one bit of configuration. And we have that inside a project CLJ as well. So check this out afterwards if you're interested in this kind of logging stuff. Another quick thing that we do is daemonizing. So when you're deploying an application, you usually end up with an Uberjar on a system somewhere, and there's quite a few ways of deploying it, of actually running that Uberjar. The way that we do it, which we kind of like, is we use Commons daemon. It's a Apache project that has an interface that you implement with 4 methods: init, start, stop, destroy. Pretty basic stuff. It's not like Tomcat or anything like that. It does just one thing very, very simply. So you implement this, and it turns out that this works really well with component, because in init, you can construct your system using some kind of config file coming in from the file system. And then you can store that, and this is the one bit of global state we have. We have no global state in our system except for this one system reference. And the only reason we have that is because Commons daemon calls init first and assumes that you mutate some global state to create the system, so that afterwards it can start that system. So here's our system, which is nil when we start, and then we initialize it, and then we call start. And all we're doing here is we're just altering that root var and calling component start on the entire system, which will then go through every component in the right order, start everything up so it's all ready to go. And then there's also stop and destroy. And so your access to this is via the program JSVC, which is just a binary running on the system. You can tell it what user to run as, you can tell it what out file to use, Java configuration, and then finally you just give it the class where that interface is implemented and start it. Commons is cool. I think, wow, I had a lot more stuff to talk about, but I'll have to cut it short. I guess the one other thing I do want to mention is that infrastructure as code gets a lot more important as you grow. When you've got one application, one Uberjar to deploy, you can SCP it to a server and run it. But when you've got 20 services running on hundreds of nodes with queues and databases and load balancers and monitoring and logging and all this stuff, you want to be able to spin up a new service like that. You want to be able to say, all right, I'm going to pull these components together and create an Uberjar out of them, and then that's a new service that I'm going to provide to my customer. If you're not automating the creation of the logback XML, of the load balancer configuration, of how many machines to deploy it onto, if you're doing that via hand, you're going to be scared of creating new services. It's going to be like a time-consuming thing full of errors. Automate as much of that as possible as early as possible, and it'll make your lives a lot easier. So as an example, here's the stuff that we have to do as part of configuring a new service, and we automate all of it so that we can. And we actually deploy all of this from a REPL. And if you want to hear how we do that, you can come and find me afterwards, because I'm not going to recommend the technology in public. So anyway, thanks for listening. Here is the code samples. I would highly recommend reading Release It. It's a book by Mike Nygaard. It'll scare the crap out of you when you're thinking about creating big systems, because it tells you all the bad things that can happen, but you should read it. Watch Component by Stuart Sierra. It goes deeper on what component is. Language of the System by Rich Hickey was behind a lot of our design of our overall architecture. And if you do want to learn more about infrastructure as code and DevOps, which I highly recommend you do, the Phoenix project is a great place to get started. Thank you.